Hello guys, this is Prime Concept. In this video, we want to consider and continue with the series we started on thermal physics. We are already considering gas laws. In our previous video on gases, we considered the Charles law. We're actually looking at ideal gas laws. Remember I mentioned that you can have ideal gases as well as you can also have real gases. So, but these laws that we are considering, the Charles law, Boyle's law, Avogadro's law, and so on. These laws are applicable to ideal gases. And we established that one of the concepts or one of the conditions or the conditions that makes for an ideal behavior for gases is that the temperature should be high and then the pressure should be low. So under a condition of high temperature and low pressure, a gas would behave ideally, and that gas would obey these laws we are considering. So in this video, we want to consider the Boyle's law, look at some of the concepts around Boyle's law, state the law, look at the graphical illustrations and so on, and then take an example. So do well to stick with me in this video till the end and you will get concepts from these things. Now, Boyle's law is a law that relates volume and pressure, or you can say pressure and volume. So, and Boyle's law states that at constant temperature, the volume of a fixed mass of gas is inversely proportional to the pressure. I would repeat that. At constant temperature, the volume of a fixed mass of gas is inversely proportional to its pressure. Is inversely proportional to its pressure. You can still say that the pressure is inversely proportional to volume. It's still same thing, right? Because both of them are inverse to each other. So at constant temperature, the volume of a fixed mass of gas is inversely proportional to the pressure. That is to say, when you increase the volume of a system, the pressure would increase. What does then? The pressure would decrease, right? That is what the law is actually saying. Volume and pressure are inversely related. So when volume is increasing, pressure is decreasing. When volume is decreasing, pressure is what? Increasing. So that is what it is saying. So what is the mathematical relationship for this law? So it is given mathematically as V inversely related to pressure, which is 1 over P, right? Yes, so that when you remove this proportionality sign, we're going to introduce a constant of proportion. So we'll have that V would be equal to K over P. So that when I cross multiply to make K the subject, I'll have that K becomes this times this is what? PV. So we have that PV, the product PV is what? Is a constant. So this means whenever you multiply pressure and volume, the number would always be fixed to be a constant, no matter what you have for P and V. So I can write this as P1 V1 equals what? P2 V2. I can still say equals P3 V3 equals P4 V4 and so on. So this is the mathematical relationship for Boyle's law. And there are certain things we should know about Boyle's law that makes it unique. So I'm going to write them as deductions from Boyle's law. There are certain deductions that are important to note, which most exam bodies like JAMB, WAEC, your undergraduate exam would be asking, right? Yes. Number one is that Boyle's law holds under the condition of what? Of course, this is the first one I would mention is general for all the gas laws. But let me mention, number one is that Boyle's law holds under a condition of high temperature and low pressure. So Boyle's law would hold under a condition of high temperature and low pressure when the gas is subjected to this condition. So if you have a condition of low temperature and high pressure, then the gases will deviate and they will no longer obey Boyle's law. So this is very important for you to note. Then number 2 point I want you to note is that Boyle's law considers the fact that temperature should be kept constant. So it means that for Boyle's law to hold, then temperature should be what? Kept constant. Somebody may say, you say temperature should be kept and you're saying high temperature. Yes, of course, the temperature should be high and kept constant at that point, right? Yes, so under a condition of constant temperature, temperature should be kept what? Constant. Of course, if you understand your thermodynamics, you would know that a process that considers constant temperature in thermodynamics, that process is known as what? An isothermal process. Isothermal process. So Boyle's law is a law that follows the isothermal process. An isothermal process is a constant temperature process. Now, number 3 point I want you to note is that the mass is fixed. The mass is kept constant also. So the mass, invariably, the number of moles is fixed or kept constant. Anyone, still same thing. So of course, for you to keep the mass constant or the number of moles constant, it simply means that you are working with what type of system? You are correct. You're working with a closed system. So the system involved is a closed system. Remember, in thermodynamics, we have 3 types of systems, right? The open system, the closed system, and the isolated system. So we're working with a closed system so that our mass can be kept what? Constant, right? Yeah, these are certain points we should note. So these are certain points we should note about Boyle's law. Very important. And the next thing we want to consider very quickly is the graphical illustration. A graph that would show us the variation between volume and pressure. Remember, we mentioned that volume is inversely related to pressure, meaning that as volume increases, pressure decreases, or as pressure decreases, volume increases, vice versa. So let's look at the graphical illustration for this law. So we can put down about 3 different graphs for Boyle's law. So graphical illustration. So number one is a graph of V, the volume, against pressure. So we want to consider this as the first case. When you plot a graph of volume against pressure, of course, it's still going to be the same as a graph of pressure against volume. So both will still be the same. So when you plot graph of volume against pressure, what would be the shape of that graph? So this is what you would have. These are volume. These are pressure. So if I plot this, it's going to give me a curve. Remember, what you have is volume is actually a constant over pressure. So volume and pressure are inverse. So you expect that it's going to be a curve like this, a rectangular hyperbola. This is a hyperbolic curve. So we call this a rectangular hyperbola. So that is what you have. So anyway, you should note that is a hyperbola, that is the shape. Now the next I want to consider is a graph, that is number B, a graph of volume versus 1 over pressure, which is going to be the same as pressure versus 1 over volume, still the same shape. Because this first one simply illustrates the fact that as you are increasing the pressure, the volume is doing what? Is coming down, you can see. At this particular point, let's say this is 1, this is 2, this 3, this 3, and so on. So at this particular point, you can see your volume, right? Yeah. At this particular point, you can see your volume. So when this pressure is increasing, volume is dropping down. At this particular point, let's say this is 0.5, you can see your volume is high at 0.5. When you increase to 1, your volume came down. When you increase your pressure to 2, your volume came down. So that is what you have. As your pressure is increasing, your volume is dropping. Or as your pressure is dropping, your volume is increasing, vice versa. Now we want to look at a graph of volume against 1 over P. So they are not the same. This is volume against P, but this one is volume against 1 over pressure. So this is obviously going to be a straight line because there's going to be no power here. So I have V against 1 over P. Now somebody may ask, how do we know when you're going to have a straight line or a curve? One of the easiest way I teach my students to know when a graph should be a straight line or a curve is, for example, this is the relationship between volume and pressure for Boyle's law, right? So you can clearly see that this thing can still be written as V equals K times P to the power minus 1, right? Now, if I want to plot a graph of V, which is volume, against pressure, you would notice that I'm just plotting volume and pressure, but this pressure is carrying a power. Since your pressure is carrying a power, but I'm only plotting the volume and just the pressure, not the power, it simply means it's going to be a curve, right? When you plot a graph of this and this quantity without including the power, it means you would have a curve. So I plotted in this first case volume against pressure. I didn't include the power. But in this second case, I'm plotting volume against 1 over pressure, which is still the same thing as volume against P to the power minus 1. So you can notice in this second case, I'm plotting volume against pressure together with the power. So when you consider together with the power, you're going to have a straight line. So this is a simple way of knowing when you should expect a curve or a straight line. When you are plotting together with the power, you're going to have a straight line. But when you're not considering the power in your plotting, you are plotting only the quantity, ignoring the power, then you will have a curve. So take note of that. So plotting volume against 1 over P, I would have a straight line that goes through the origin like this. So this is what I would have. So which simply tells you that your volume, sorry, this is a mistake. Let me quickly correct this. This graph, of course, what do you think this what I've drawn is showing? Simply showing you that both of them are increasing, right? Yes. This is correct. This is correct. So going through the origin. So this is what you would have when you plot volume against, this is 1 over pressure actually. So it's going to be a direct relation. So when you increase 1 over P, not pressure, please take note of that correction. We are plotting 1 over P. So when 1 over P is increasing, the volume would increase. When 1 over the pressure is increasing, the volume is increasing. So that's why you have a straight line like this, because you can see that if P is small, 1 over P will be big. So that is it. Then the third graph we have is a graph number C of PV versus P. So when you plot a graph of PV versus P, or you can still see PV versus V, both of them will give you the same shape. So if I plot a graph of this product, PV versus pressure, or PV versus volume, I would have a constant graph. Now this is what I have. This is PV, this is P, right? Or V. So any one of these you have. And when you plot this, remember from Boyle's law, we have that PV is equal to constant. So it means that this graph would maintain a constant value on the PV axis. So it's going to be that constant K. It's going to maintain that constant value K on the PV axis. So that whatever the value of P would be, as you keep increasing P, the value of PV is just constant. It might be 2. So no matter the value of P, this would remain 2. No matter the value, so the same thing, it might be 3, no matter the value of P you put here, it will remain that 3, it will remain constant. So these are the 3 graphs for Boyle's law that you need to know. And most of these things you would see them in your exams, the graphical illustrations. They would ask you which one of these graphs does not represent the Boyle's law, right? Yeah. So the next thing I want to consider now quickly is a quick and a simple example under Boyle's law so that we can internalize the concept. So let me put the question on the board. So we have our first example here, right? Yes, and this is actually a question from one of the exams of JAMB, I think 1999. So we want to look at this. The question says a gas at a volume V0, that is the initial volume. So I'm going to say my initial volume V1 is equal to V0. So a gas at a volume V0 in a container at pressure P0. So the initial pressure P1, I'm going to call it P0 like they give us, is compressed. That gas is compressed to 1/5 of its volume. That is to say, when they compressed that gas, the final volume of that gas, V2, became 1/5 of the original volume. That is to say, it became 1/5 of the original volume, V0 of its volume. Now, the question says, what will be its pressure if it maintains its original temperature? So temperature is kept constant. What will P2 be? So this is what we're trying to find. So quickly, you would recall that Boyle's law says P1 V1 equals P2 V2, right? Yes, so that when I substitute this, P1 is now P0, V1 is now V0, then P2 is what I'm looking for, then V2 is 1/5 V0, right? So quickly you would notice that V0 can fizzle V0. So I'll be left with P0 equals P2/5. So when you cross, you have that 5 would multiply this. So you have 5 P0 equals P2. So it means that the pressure would be what? 5 times the initial pressure. When you decreased the volume by 5, the pressure increased by a factor of 5. So you can see Boyle's law still verifying itself. Now let's take problem number 2. So we have another question to analyze under the Boyle's law. So the question says the equation P raised to power x, V raised to power y, T raised to power z equals constant is Boyle's law. So that is to say, this equation would represent Boyle's law under the condition that x, y, and z should take what values. So this can represent Charles' law. It can also represent Boyle's law. So for this equation to represent any of these law, these values of x, y, and z should be unique. So what are the unique values of x, y, and z that would make this equation represent Boyle's law? Now, the first thing you want to ask is, what is Boyle's law? Boyle's law says that P V is equal to what? Constant. This is Boyle's law. Boyle's law, PV is constant. So which simply means that if you check here, you notice that there is no temperature in this because temperature is kept constant. Now, one of the things I want to do, if you recall in your maths, anytime you have any number A raised to the power of 0, this would be same thing as what? 1. So I'll be using this idea. So it simply means if I write temperature T raised to the power of 0, this is same thing as 1. So that when I multiply 1 by anything, it will give me same thing. I can introduce temperature here. So I can still say this is Boyle's law, P, V times T. But when I'm introducing temperature, I should give it a power of 0. So that when T raised to power of 0 is 1, 1 times PV, I'll still get back PV. So when I do this with T taking the power of 0, it means this is still Boyle's law, equal to what? Constant, right? Now, of course, you know, whenever you write a variable and there is no power, obviously, it simply means that the power that is there is what? 1. You are very correct. So now looking at this and comparing this to this standard form, quickly, what can we tell? You can quickly tell that x is what? 1. So x is 1. That is the power on P, which is 1. y is 1 also, and then z is what? Is 0. So these are the values of x, y, and z, so that this would represent Boyle's law. Now let me give you a quick one. If this should represent Charles' law, what would be the values of x, y, and z? Drop the answer in the comment section. Let me know if the concept is clear to you. And let's take our third problem here before we stop this video. So one of the things we want to also quickly point out for Boyle's law is that Boyle's law is also a law that can relate to work done. So we can relate Boyle's law to work done, right, in terms of pressure and volume. And quickly I'll be showing you how that Boyle's law will relate to work done. Now, if you recall, work done is the product of force times distance. So let me call that distance the x, or let me still say, better still, change in x, right? Any one of them would go. So this is work done, force times distance or displacement, right, in the direction of that force. If you recall, you would know that pressure is force over what? Area, which would simply imply that force is PA. Force is pressure times area. So I'm going to replace this. Then I would have that my work done is going to be what now? Pressure times area times change in x, right? Yes. Then I can see something unique around here. Area times change in distance is going to give you what? Volume, right? So I have that work done can be written as pressure times change in what? Volume. So this is actually saying that work is pressure into V2 minus what? V1. So you can still see that this still relates to Boyle's law, PV, right? So this is still Boyle's law. So Boyle's law is a law that still relates pressure, volume to what? Work done. So they tell you to find work done by a gas tomorrow, and this is what you're going to use. So I'm going to take a problem solving work done under Boyle's law. Let me put the problem. So we have this problem under work done. So the question says a gas at the pressure of this. So the pressure is given to us. A gas at a pressure of 10 to power 5 Newton per meter square expands from, so where it is expanding from is your initial volume, expands from V1 equals 0.6 meter cube. So take note, meter cube is the SI unit of volume, so that is why we're using it here. And then this is the SI unit of pressure, Newton per meter square. So also there is no need for us to convert. So from this to this, so our V2 final volume is 1.2 meter cube at constant temperature, which tells you that it's Boyle's law. The work done is, so we're trying to find the work that is done, and it's very simple. So what is work done? We just derived. The work done is pressure times V2 minus V1, right? Yes. So that the work done becomes what now? P, which is 10 raised to power 5 into V2 1.2 minus V1 0.6. So that when I solve this, I'll have 10 to power 5 into this should still be 0.6. So that when I multiply, I would have that my work becomes 6.0 times 10 to power 4 joules. So this is my answer, right? I believe this concept is clear. So at this point, we are done with Boyle's law. So if you still have any question, anything you want me to clarify under the Boyle's law, do well to drop your question in the comment section. I will check and respond to it. So thanks for following Prime Concept. Do well to subscribe if you are yet to subscribe. Like this video, comment, and share with 10 of your friends. Tell them this is Prime Concept. Thank you.